Okay, I see only one person in the room. I thought I saw somebody else. Okay, I see somebody in the room.
Good morning.
Good morning. Did you get my message? I guess everybody should get my message that there's a lecture today.
I got it.
Yeah, I guess people are. I see another person, David Alexander. Would you like to show your face, David?
Yeah, just a sec.
Okay, see Jonathan. So maybe more people will drift in to the room.
We don't have a homework assignment due this weekend, do we?
No, you don't have one due today.
Okay, cool.
You will have one due next Friday. I will give out one today.
Okay.
So you get a week's break,
Cool.
more or less a week's break. Chen Liu Zhou, would you like to show your face? Chen Liu? Lee 2864, I don't know who that is. Would you like to show your face, Lee? Okay. I would encourage everybody to show your face so that you give a more human touch to the classroom. Hi, Zheng Liu. And then when you see each other on outside the classroom, maybe you can say, hi, I saw you in ECE 604. And maybe we have something in common in terms of interest. Okay, I see Lee 2864. What is your full name, please? I forgot. Oh, your mic is off, sorry. Your mic. You don't have a mic. Okay, let's get started then. What is your full name, Lee?
Changhyun Lee.
Or Changyung Lee? Okay,
Yep.
sounds Korean to me. Okay, let me share my screen. And then I have a PPT slide that I'm sharing with you. Today we will talk about transmission lines. Again, we started on transmission lines in the last lecture. We have more discussions on transmission lines, mainly on the application aspect of transmission line theory. So we will start with talking about a terminated transmission line. We did not talk about termination of a transmission line. We just say that if you have a transmission line infinitely long, what kind of solutions you can have on a transmission line. And we discovered that we could have traveling wave solutions because the equations that we find that the voltage and the current satisfies are the wave equations. So if I were to write them again, it would be like the Z, BZ, these are phases. And then we found that the current also satisfies the one-dimensional Helmholtz wave equation. Okay, we found this to be true. And then, hence, if you have a transmission line, the solution are traveling wave. For instance, you can say that Vz is of the form of V plus e to the minus j beta z, the traveling wave to the right, and then e to the minus j beta z, which is a plus j beta z, sorry, which is a traveling wave to the left. Okay, and then the current is also of the form of I plus e to the minus j beta z plus I minus e to the plus j beta z. And we discover something very important, that is V plus over I plus has the value of Z naught, called the characteristic impedance of the transmission line, which is given by LC. And then we found that V minus over I minus has a negative sign, Z naught, which is minus square root of L over C. So those were the important preliminaries that we have studied. So let's see what happens if we put a termination at the end of the transmission line. If we do have a termination at the end of the transmission line, we cannot have just one solution of the wave traveling to the right. Any wave that is traveling to the right will be reflected. So the solution will be more fully represented as a right traveling wave plus the left traveling wave. Whereas if you take this away and make this transmission line infinitely long, you can have a purely right traveling wave or a purely left traveling wave. Okay, so we would like to put this load over there and then decide on the ratio between V minus and V plus. And how do we decide that? Well, we are going to say that the voltage at Z, again, the voltage at Z equal to 0, which means that the left traveling wave voltage at Z equal to 0, you can see the transmission, the equation on the previous transmission line, previous slide, okay, must be equal to a gamma L times V plus Z equal to 0. What we have done is that we say that Vz is V plus Z plus V minus Z. In other words, given the voltage that is right traveling and left traveling, we'll call this V plus Z, and then we call the other one v minus z. Okay, and once we do that, then we can set v plus z and v minus z to be 0, and their ratio will be determined by this constant gamma L. Okay, so say if we have this thing, then what I should say is that v plus z equal to 0. This is a very bad notation, because if I call this v plus z, if I set z equal to 0, it would just be v plus. And let me call that a plus instead. Okay. And then if I were to take this number and set z equal to 0, I will get v minus, which is again a rather bad notation. I will call that a minus instead. And then I will have the relationship that if I plug this in here, I will have the fact that a minus is equal to gamma L a plus. A plus and a minus being the amplitudes of these waves as they're traveling to the right and traveling to the left. Okay. So with this relationship, I can actually write down the fact that Vz, which is a plus e to the minus j beta z plus a minus e to the plus j beta z. I'm writing the same expression as I did before, but with v plus and v minus being replaced with a plus and a minus. And if I were to say that a minus is gamma L times a plus, I can rewrite this equation as with a plus outside. And then I can put everything else back inside. And then because a minus is gamma L a plus, I will have to leave behind a gamma L there. Okay. So this is the relationship that I should have now. And I can find the corresponding current IL, IZ, either by using these formulas that I have before, okay, using those formulas that I have before, or I can directly use the telegrapher's equation. And using the telegrapher's equation, I would use the fact that IZ, or I can use, let me write it down here. Telegrapher's equation says that dV dz is minus j omega Li. So I can differentiate the above equation with respect to z and divide by j omega L. And then I should get a new formula. And that new formula is not that different. And if you simplify that new formula, you will have a z naught appearing somewhere. And then e to the minus j beta z minus gamma L e to the plus j beta z. Okay, this minus sign is very, very important, because for the voltage, the right traveling wave and the left traveling wave has plus gamma L. But for the current, the right traveling wave and the left traveling wave are related by the number minus gamma L. So now if I were to define a reflection coefficient, a general reflection coefficient, which is just the ratio of the voltage traveling in the negative direction with respect to the voltage traveling in the positive direction. What I do here now is to go back to my definition of V plus and V minus. If you recall, I call this, let me go back here. I call this term V plus and V minus, and later on I replace this B plus and B minus with A plus and A minus. And if I do that, then if I take the ratio of these two waves, again, these two waves, and if I call this For instance, if I were to use this slide to prove my point, this would be V plus Z, and this will be V minus Z. Okay, then V minus Z over V plus Z, we just take these two terms and take the ratio, you will have A minus e to the j beta Z over A plus e to the j beta Z with a minus sign here. Okay, let me write this properly, minus j beta Z. And what you have is that A minus over A plus, as we have defined before, is just the reflection coefficient. Okay, so A minus over A plus is gamma L. So this is gamma L e to the 2j beta Z. So the factor of 2 is very important. This is called the general reflection coefficient. Okay. This general reflection coefficient is just the ratio of the left traveling wave to that of the right traveling wave at the location Z. Okay, so it's a function of Z. But then if you were to set Z equal to 0, then this term will become 1. Okay, so you will have gamma Z equal to 0 should be gamma L. Okay, gamma L would be just this reflection coefficient that we have defined earlier. And then we will also have V Z equal to 0 over I Z equal to 0. Okay, if we take V set to 0 and divided by I, and then with Z set to 0, I take the ratio of these two terms, you will see that the A plus cancel each other. Z equal to 0 makes all this to become 1. And then I would have this to be equal to 1 plus gamma L over 1 minus gamma L. And then there's a Z naught here, when I take the ratio, and that Z naught will appear to be Z naught over here. Okay, but V at Z equal to 0 over I at Z equal to 0 is also equal to gamma L. Because there's a definition of what gamma L is. Okay, because if you were to take the, oh, sorry, not gamma L, it should be ZL. Okay, if you take the voltage at the end of the transmission line, take the voltage at Z equal to 0 divided by the current at Z equal to 0, that is just equal to the impedance at this point. So this identity is true. And now we have a very interesting formula, which says that this is equal to that. Okay, this is equal to that, which means that we have, you can solve for gamma L quite easily, and you can also write this equation as 1 plus gamma L, 1 minus gamma L is ZL over Z0. Okay, take this equation. And usually we call this to be the normalized load impedance. ZL is the load impedance. ZNL is a normalized load impedance. Let me write it down. Normalized load impedance. And what this equation says is something very important. It says that once you know the normalized load impedance, you can solve for gamma L, or you can do the vice versa, which is that once you know what the reflection coefficient is, you can solve for ZNL. So I can invert this equation also. If I invert it, it's high school algebra, so I won't go into the detail that the reflection coefficient is ZNL minus 1 over ZNL plus 1. And I can also, if I use back the definition of ZNL, what it should also be written as ZL minus Z0 plus ZL plus Z0. Okay, so the reflection coefficient can also be written as such. So this is a wonderful formula which is very important. What it says is that once you know the reflection coefficient, you can solve for the normalized impedance. And once you know the normalized impedance, you can solve for the reflection coefficient. But we can define something more general than this to make things more useful. So we would define a generalized impedance, which is the ratio of the voltage to the current at a point Z in space. So this is a concept that you never have in circuit theory, that you take any point in the transmission line. Take any point in the transmission line. There's a voltage there, there's a current there. And you can take this ratio that would define the impedance at that point. Whereas in circuit theory, it says that all the voltages on this line will be the same and all the currents on this line will be the same. But if we have wave physics, what it says is that the voltage here is different from the voltage there. The current here is also different from the current there. So each point in space has a generalized impedance that you can actually now derive. Okay, you take the ratio of this thing, which is these two equations over here. You essentially take the ratio, okay? And if you take the ratio, then you will have this, I wouldn't go into the detail, but then if I were to take the ratio of this expression that I had in the previous slide, okay, let me see if we can show the previous slide here again. You may take the ratio of these two terms, the A plus would cancel, and then I will have this rather complicated looking expression. And it will be Z0, 1 plus gamma L. Let me write the full one first. The full one is just this ratio. Plus gamma L e to the plus j beta z, okay, over e to the minus j beta z. And remember, the minus sign is very important. If the minus sign is not there, then this ratio would just be 1. So the minus sign is very important because the current assumes the minus sign. So I hope you can see that. Take the ratio of these two terms, you get this complicated expression on the right. And then what you have now is that I can simplify this expression by taking the phase factor out so that they cancel each other. And if I take this phase factor out, then this would be given an added phase. I hope you know how to do this algebra, that if I were to take the phase factor out, then what I have is 1 plus gamma L e to the 2j beta z, and then 1 minus gamma L e to the 2j beta z. Okay, I hope you can follow this algebra. You take the phase factor out, then you have to add the phase back here to make it into a 2, and do the same thing to the denominator, and this is what you should have. Okay, and then we can write this in a very suggestive form as a relationship between the generalized impedance and the reflection coefficient. Let me call this reflection coefficient gamma z. Okay, so where gamma z is called the generalized reflection coefficient is gamma L e to the 2j beta z. Can you see that? So this relationship is just like what we have derived before, the relationship between impedance and reflection coefficient. There we derive over here. Once you have impedances, you have a ratio a relationship to reflection coefficient. And once they have reflection coefficient, you have a relationship to the impedances. So this is another relationship, but this relationship is going to be applied to every point in space. Every point in space has a different impedance from the other point in space because of the wave nature of the problem. Okay, so let's take this further. Okay, if you take this further, then this is very similar to your load impedance relationship. You can also invert this relationship as we did before, and then gamma z would be just equal to the normalized impedance. You can call this normalized impedance at the point z minus 1 over znz plus 1. Okay, let me emphasize that this is lowercase z. Okay, I can invert that equation where zn z is just z of z over z naught. Okay, I can invert that equation quite easily. I won't go into the detail, but then you can actually now have a generalized impedance, and it will be a function of z because of the wave nature that we are dealing with. And you can write this relationship more explicitly if you want to. Say if you have this relationship, and you can actually use the Euler's formula. Euler's formula say that e to the I, or not I, we use j here at this point. Jx is cosine of theta plus j sine of theta. Okay. Then you can express everything you have in the exponent in terms of sines and cosines. They should be a theta here, sorry. Okay. You go to the algebra, which I'm not going to go through right now, that you can actually convince yourself that if you change z to minus L, okay, which is this picture I have over here, that is, if you were to look at the impedance at this point at z equals minus L, okay, not the impedance at this point, but z minus L point, then you can derive a relationship for this thing, which I'm not going to derive, but just give you a verbatim, because it's high school algebra to derive it. You can derive it in your homework. Tangent of beta L over z naught plus JCL, tangent of beta L. Okay, so this is a good formula. If you have a calculator, you can punch the length of the transmission line into this formula. Beta is, of course, omega over V, and in this case, it's omega square root of LC. So if you know all the parameters of the transmission line, you can punch the numbers into this formula and obtain the impedance at the minus L point. Of course, Z naught is the characteristic impedance, and Z naught, as we know, is equal to square root of L over C, where L is the line inductance and C is the line capacitance. Any questions so far? Okay, so these are all formulas that are very useful. And the next topic I'd like to talk about is actually when you have shorted termination. That is, if you take the transmission line, instead of putting a load at the other end of the transmission line, you put a short. And this has many engineering applications. And if you do that, what you do then is, let me move this slide up so that it will be next to the previous slide. So if you take this formula and change ZL to 0, Okay, so if I take the previous formula from the slide and change the load impedance to this to be 0, which is the impedance of a shorted transmission line at the end. And then you can look at that formula. This term will go away, that term will go away. And then you can see that ZL is actually Z minus L would be equal to J Z naught tangent of beta L. Okay, L is the length. This point over here. Okay. So if you plot this formula, Z naught is a real number for a lossless line. I remind you that Z naught is a real number, is given by this. And then it looks something like that. It will be like the plot of a tangent. And it will have an inductive part and a capacitive part. And when the length is very small, then the transmission line will have an impedance that looks like that of an inductor. However, if you make the length of the transmission line longer, it actually can resonate. And when it resonates, it will have infinite impedance. Just like an LC tank circuit, you probably have seen this before, that if you have, say, an LC tank circuit, you probably learned that when this thing is at resonance, you see an infinite impedance. So you can say that this point here is when this circuit hits a resonance point, and it will have infinite impedance. The interesting thing about transmission line is that the moment you go right to the right of this resonance point, you have a negative reactance. You have a negative reactance. If I call this to be something like Jx, okay, X to be the reactance of the line, then you can see that when something is negative, you probably learn from your circuit theory that impedance of a capacitor is 1 over J omega C is minus J 1 over omega C. So a capacitor has negative reactance. So we call that this part of the line is capacitive. Whereas if you have an inductor, you probably know that the Z of an inductor is J omega L from the circuit theory course, and that the inductor has positive reactance, and hence you call this part of the line to be inductive. And it swaps back and forth depending on the length of the line, because when something is inductive, it means that there's a lot of magnetic field stored in the system. When there's something is capacitive, it means that there's lots of electric field storage in the system. And it swaps back and forth because there could be charge accumulation and standing wave or wave pattern on this transmission line that give rise to this standing wave pattern. What is remarkable is that when you have a very short line, okay, you know that when beta L is very small, you can approximate this as beta L. It's a trigonometric identity that you learned in high school. Okay, the argument of a tangent function is small. It can be approximated by that. And then you have this formula, Z of minus L is J Z naught Z naught beta L, okay? And if you recall what Z naught is square root of L over C, and then beta is omega LC, and then you have an L, and then the C cancels, and then you have this being equal to approximately J omega L, okay? So you can think of this as kind of a line inductance times a small length, give you the effective inductor of this very short transmission line if you make it very short. That is reasonable if you do a sanity check. that if this line is very, very short, then if you were to send a current into this line, the current would be huge because it's shorted at this end. If you drive this, say, with a voltage source, and if this current is huge, it will produce a strong magnetic field, making this transmission line inductive. Okay. So any question on that? If not, then let's go to the next example, which is that of the open termination. That is what happens if I were to let me move this up. Sometimes, well, let me leave it down here for the time being. So what happens now if I let the other end of the transmission line be open circuited? In this case, ZL is equal to infinity. Okay, you can go back to your formula that we have derived previously for this general case. And if we make ZL infinitely large, this term will dominate over this term. And if you make ZL infinitely large in the denominator, this term will dominate over this term. And if you go through all the thought processes and drop the unnecessary terms, you will find that at this point, you have actually an impedance that looks like, let me see what I have now, that Z of minus L would be minus J Z naught cotangent of beta L. Okay, cotangent because I have a tangent in the denominator. Remember, if I go back and look at this formula again, I have a tangent in the denominator that when I invert it, it becomes a cotangent. So you will get this formula. Okay, and again, if you plot it, it will look something like this, that if this line is very short, it will look capacitive. And you can do a sanity check on that. Well, should it look capacitive? Well, if you have a very short piece of transmission line, if you connect the voltage source to it, there will be strong charge accumulation on this small piece of metal, and there will be electric field in between, and you have this kind of thing. And again, it goes to positive and negative, positive and negative. Okay. The next thing I'd like to talk about is a graphical calculator called a Smith chart. Smith chart is a very useful way of solving this formula, because in transmission line theory, okay, we essentially have to solve this formula over and over again. Gamma L is equal to Zn minus 1 over Zn plus 1. Zn is 1 plus gamma L, 1 minus gamma L. Okay. We will have to solve this formula over and over again. It is a formula that allows you to go back and forth. And even for the generalized reflection coefficient, we have something like this too. So this formula is everywhere in transmission line theory. Instead of using our calculator to do this, every time we need to punch numbers into this formula, we can use a graphical calculator. The graphical calculator allows us to do this calculation rapidly without resorting to a, I guess, an electronic calculator. And it works graphically in this manner, in the sense that if you were to look at this formula, it is called a bilinear map. The characteristic of a bilinear map is that it maps circles into circles. So if you think of the right-hand side, Znz is a complex number, and that complex number can be written as Rn plus Jxn. It will have a real part increasing on the real axis, and then the imaginary part is increasing on the imaginary axis. So you can think of any impedance that you have in this world can be put as a point on this complex plane. Then what the formula does is that it takes a point on this complex Z plane and maps to a point on the complex gamma plane. So the gamma plane will have the real part and the imaginary part. It will correspond to one point on the left-hand side of this formula, or one point on the left-hand side of this formula. And since these are bilinear maps, that maps circles to circles, you can think of a straight line being a circle with infinitely large radius. So this line over here, I don't know if you can see it. This is the imaginary axis line on the complex Z plane. That will map to this line over here. Okay, can you see that? Where this is the infinity point. So what the Smith chart does is take the points at infinity and wrap them around and put all the infinity points at this point over here. Can you see this visually? If you're a contortionist, you can see this, that you're actually contorting the chart on the left, take the points at infinity and wrap them around into a point on the right-hand side as such. And all the points that you have on the left-hand side will map to points on the right-hand side. And what is most notable is that if we have resistive loss, if Rn is a positive number, it says that we have an impedance that is lossy at the end of the transmission line. Okay, this is a lossy transmission line. The reflection coefficient has to be less than 1 by energy conservation. Okay, by energy conservation, it has to be less than 1. So everything on the right-hand plane, right half plane, maps to the circle, which is a unit circle on the complex gamma plane. That means that energy conservation applies. Energy conservation prevails. Reflection coefficient can never be larger than 1. And then you can see that the imaginary line over here, this line, which is the line where the reactance is positive 1, maps to this line over here. Again, straight line maps to circles, or circles map to circle. You can imagine a circle over here, okay? But this is only part of the circle. And then this line maps to this line over here. And you can actually go through the mapping, and this line maps to this line over here. This line maps to this line over here, and so on and so forth, okay? And another notable fact is that when the impedance is 0, that means that you have a short circuit. Then the reflection coefficient has to be -1. You can go back to looking at this formula, that if the impedance is 0, the reflection coefficient is -1, which is what we expect. Okay, then 0 impedances map to this point. And if the impedance is infinitely large, then it will map to reflection coefficient of 1. So if you let Zn be infinitely large, which are those points at infinity, they map to that point over there. And if you let the normalized impedance be 1, okay, which is this point over here, okay, then that point maps to this point. This point is the origin of the complex gamma plane. It says that when you at that point, there's no reflection coefficient and the reflected wave is 0. Okay, so that is called the matched load. In that case, the load is matched so that there's no reflection of the reflected wave. And these charts are available commercially. You should be able to get a better copy than what I have shown on the figure over here. You can read these things actually to quite high accuracy, and it's good for most engineering applications. But Smith chart is going to stay with us for a while, because we actually can do mental calculation with it in our head. The reason why we can do mental calculation in our head is that if you have a load, and then if you look at the reflection coefficient away from the load n, there should be a factor of 2 somewhere else, 2 beta L. Okay, if you look at this formula that we have previously defined, which is that well, that the generalized reflection coefficient at the location Z is the load reflection coefficient times this phase factor. Okay, so if I set Z to minus L, I get this formula over here. So it tells me that once I know where the reflection coefficient is on the complex plane, I can add this phase to this reflection coefficient and get the actual reflection coefficient at different parts of the complex plane, which means that if I know gamma L, say a point on this Smith chart, and if I add a length to it, I have to add a negative phase. Okay, I have to add a negative phase because what I have in the next picture, okay, if I add the length, I have to add a negative phase, and adding a negative phase would mean that I will have to add things in this direction, okay, for increasing beta L because of the negative phase that I have to add to this problem. Did I get it right? I should go in the other direction. I'm sorry. If I add a negative phase, I should go in the opposite direction, not in this direction. Okay, so I would have to move in this direction. And that actually is shown on the peripheral point on the Smith chart. If I can blow this up, if you look at this, I cannot make it bigger. But if you look at this blown up, you can see that it tells you which direction to move. So those are very important things for engineering applications. And the reason why we have a factor of 2 is because the wave has to travel a round trip of 2L. If this is L, then the wave has to travel a round trip of 2L. So you get this phase of 2L added to the load every time when you have this, okay, this thing added then. And also on the Smith chart, people like to think in terms of wavelength. So because of that, this formula is always written when you take beta is equal to 2 pi over lambda. You plug that in there, then you can rewrite this formula as 4j pi L over lambda, which means that because of the factor of 2, if you were to go to add a, say, a half wavelength, okay, if you add a half wavelength to your transmission line, it will take you one full circle around. It will get you 2 pi. So for instance, if L is lambda over 2, then this is just minus 2j pi. Okay, and it takes you a full circle around the Smith chart. So you can play this kind of mental images in your mind and say if you were to add a quarter wavelength, it will take you to a point that is diametrically opposite to the Smith chart, and you can move all these things around in your head. Okay, and microwave engineers are very good at this. They can actually visualize this chart in their head and do calculations with this Smith chart. So there's something that we cannot get rid of because of the conveniences that it offers to microwave engineers. You can do mental calculations in your mind. Okay. So the next thing I'd like to talk about is actually the voltage standing wave ratio and voltage standing wave pattern, in the sense that if you have a voltage on the transmission line, it's not a constant because they are traveling wave. The traveling wave of this kind, e to the minus j beta z plus v naught gamma L e to the plus j beta z. Okay. So the reflection coefficient will give rise to a traveling wave traveling to the left, and I can rewrite this as v0 e to the minus j beta z 1 plus gamma L e to the 2j beta z. Okay. And then if I were to take the magnitude of this voltage, it will be voltage magnitude V0 magnitude, and then magnitude of 1 plus gamma. And this I can call gamma z if you remember. Okay, this is just gamma z because this is the definition of gamma z. Gamma z was defined to be that which is the generalized reflection coefficient at the position z, which means that if you were to look at the voltage on the transmission line, it's not a constant. And you can do this calculation. Actually, I have this calculation which you can do using a chart. So if you have gamma z, which is a complex number, 1 plus gamma z, if this point is 1 plus gamma z would be this length over here. And if gamma z is changing, gamma z, if you recall, is gamma L e to the minus 2j beta L. Okay, so if gamma z is changing, gamma z will be changing, and you can actually track the change of gamma z. It will be following this circle on the complex plane because you're just adding a phase to this number. Okay, and then you can see that this amplitude of this line would be proportional to the amplitude of the voltage. And you can see that the voltage would reach a maximum at this point. This line will reach a maximum at this point, and then a minimum at that point. And you can actually figure out that the maximum voltage to the minimum voltage, which is what we have over here. And this maximum voltage is just 1 plus gamma z. Let me put this gamma. And this minimum voltage is 1 minus gamma z. Okay, you can see from this picture that at this point, it will be 1 minus the magnitude of gamma z. And the other point will be 1 plus the magnitude of gamma z. And hence, if you can measure this voltage standing wave pattern, okay, you can measure this voltage standing wave pattern, which is called a Wiswar. The Wiswar is a way to pronounce a word with no vowel. So engineers from the microwave area would call this Wiswar, and will be 1 plus gamma z over 1 minus gamma z. Okay, and that if you have a, let me see. So if you have this ratio measured on the transmission line, you can easily invert this formula to get the magnitude of gamma z. And then you can also go through the mental arithmetics and decide that if the gamma L is a complex number, you will have to add a certain phase to move it around. And hence, by checking out where it reaches the maximum, which is this point over here, and which is this point over here, and then checking out where it reaches the minimum, which is this point over here, you can actually figure out what the phase of the complex number is by checking out where the maximum and the minimum points are. So by keeping track of dmin, okay, which is when you have to add enough phase to move this point to the other side, you can also figure out the phase of gamma z. So in other words, by measuring the voltage standing wave pattern, you can find the magnitude of gamma z as well as the phase of gamma z. Okay, and by so doing, you have the full knowledge of this gamma L. You have this gamma L. You know its magnitude, and you know its phase as well. Okay, and you know this complex number in full, and then you can find the thing. And this is just a device called a slotted line that you can put a probe inside to measure the standing wave pattern, voltage standing wave pattern. And then you can also take things out of the thing to measure the strength of the signal. And the setup is quite complicated. It's given by this diagram over here. I wouldn't go into the detail. You can read about it. And then from the strength of the voltage and the pattern on the thing, you can figure out the load. You put a load at one end of this transmission line, and you can figure out the impedance and the complex number that is associated with the impedance. Okay, I'll stop here. This microwave engineering is a very important field, and it is something that you should learn beyond circuit theory, because you know that as the frequency gets higher and as the wavelength gets shorter, even if you go and work in the microchip industry, you will have to learn transmission line theory in order to do well in the computer industry, including the microchip industry. So I would encourage you to read these notes carefully, and also read the undergraduate notes that I posted on the website from ECE 350X, and learn this knowledge well. This is kind of a revisit. I think for some of you, it will be revisiting this knowledge, because some of you have this knowledge in the undergraduate course before, but some of you might not. Okay. Are there any questions before we stop here? Any questions? If no questions, then I'll let you go. Okay. I'll see you next time then. See you Monday. Have a good weekend.